This video is about transformer circuits, and I'm going to share with you examples of what they are. And this video is about a paper that was written by Anthropic called A Mathematical Framework for Transformer Circuits. And it's part of a field that started called mechanistic interpretability, and there has been a lot of progress in it. And it's about looking at the operations of an LLM, being able to backtrack and looking at it as a decomposition of our sum over paths. So I'll go over like what that mean. I'll go over pieces of this paper. So let's start with a very simple example. Suppose you had a really simple prompt like the cat sat, and how does this how would this work? How could we use transformer circuits to understand how it outputs a probability distribution? So if you look at the cat sat, there are tokens, as you know, for each of these words, and these tokens are mapped to a vector space. So this right here is an embedded matrix, and each of the token maps to a specific column in this vector space. So what this forms, this right here, when we start off in an LLM, this right here is the first step in something called a residual stream. So as your prompt is converted to tokens and then mapped to a vector space, there are operations that are being done, and each operation you're updating a residual stream along the process. You start with the embedded matrix in the beginning. And this is what I would mark x0. So the next step after this would be x1, x2, etc. So this is the concept of a residual stream. You have raw embeddings in the beginning, then you have different layers like the attention layer where you're updating the matrix that you started with, and then you have other layers that just keep on updating until you produce logits, which allow you to produce a probability distribution. Logits are like scores. So this paper talks about residual stream is simply the sum of the output of all the previous layers and the original embedding. So that's the first concept. And let's look at an example of a very simple, like one layer LLM, and where you have one attention layer. So after you have map the tokens into the vector space, the embedding matrix, what happens in the first attention layer? What happens to the residual stream? So when you start off by producing and working with something called an OV circuit, an output value circuit. So in this case, in this example, you may have, you're going to have sat, the word sat, the token sat will attend to a cat. It could also attend to the word the. And it does so by using this matrix in a specific attention score that gets calculated using a softmax. So in this example, we're also going to move information around from the one token to another, like for example, from cat to sat. And we're also going to do this by first querying, what am I looking for? And that's what the token sat will ask cat, and then cat will respond by saying, what do I have? So this is like a query key value operation. So this operation, what happens in a specific attention head, can be modeled by this equation. In this equation, you have the attention score when you're taking a tensor product with a circuit with a set of matrices. A circuit is basically a chain of matrices. In this example, is the output value matrix. And we're multiplying it by a specific column in our embedded matrix. And we're going to look at each piece of this equation here. So the first step, as I said, this is our first introduction to our first circuit, which is the OV circuit. And this circuit is just the chain of two matrices, the output and the value matrix. So When we move information around from one token to another, we're basically going to do a specific operation. We're going to do a dimension reduction. So we're going to take a specific token, in this example, in this case, we're going to multiply it by the value token. So if I do that multiplication, it kind of looks like this. You have our column, you have the specific vector, and you're going to multiply it by our weighted value matrix, and you'll get a specific example, which is this. Oops. And so this right here is the example, and you see that it's doing a dimensionality reduction. So this is the value matrix. I'm just using this as a toy example. It may be a bit contrived, but it's something which is learned. So it's a learned, weighted matrix. So to pass information back, what we need to do is to work with our output weighted matrix, our weighted output. So in order to do this, we're going to take the result that we got and then perform a multiplication, which is going to give us a specific answer, which is that we're going to add back to our residual stream that we started off with, which is x0. So which is going to help us to get to x1, which is part of our first attention layer. So if you look at this, if you look at these are the two operations that we're doing, and if you combine WO, WV, these two weighted matrices to produce something called a circuit. So this is our first circuit. This is the output value circuit, which we could use directly to produce a specific output. So you'll see this paper talk about this. To understand these products can be helpful to think of them as passed through the model, starting and ending at tokens. So there are two important circuits that this paper talks about next, which is the QK circuit and the OV circuit, which is what we just looked at. So next thing we need to do in this equation is to understand what A is. We're taking a tensor product with that. So this was our first circuit. The next thing we need to look at is how is the tension calculated. When we calculate the tension, there is the QK circuit, which gets utilized. And let's look at that. So one token is attending to another, and what this matrix allows us to do is that it gives us information by how much is it pulling from other tokens. So for example, SAT is pulling on itself by about 0.1%, and then you have SAT is pulling from CAT 0.6%, and similarly for 0.3. So these are scores that are calculated. And how do we do that calculation? So this calculation is done by performing a matrix operation, which is going to be a query and key vector operation. So you have these two weighted matrices that are learned, the query, and the key right there. And you're multiplying it by a specific vector. So when we do this operation, we're basically going to take a score. So another thing is that you'll see in there that I'm taking a transpose. This is because of how matrix multiplication works. So if I were to distribute this transpose, it looks like this. So if you move things around this in this equation, what we could do is that we could have W and K right there as a product. And that right there is our first circuit or our second circuit, the query key circuit that we could utilize to basically calculate the score. And this is done also by using a softmax. So this is our second circuit. So what you could see is that I'm kind of like mapping the operations in terms of decomposing them as with circuits. So those were the two circuits that we looked at, and the operation that you usually do, that you do to calculate a tension score is softmax of this. So let's look at a very simple example of like a one layer LLM, which is something that's very, very simple, where you have basically some raw embeddings, you have one attention layer, and then you have logits that are produced that are help you to produce a probability distribution. of the next token. And I could write this, the paper shows you to write this as a sum over paths. So the way I am calculating x1 is like this in the second layer, in the attention layer. And I am taking into account the residual stream, the result from my previous layers, which in this case is x0. And x0 in this case is our embedding matrix because this is a one layer LLM. Something very simple to understand the operations here. So there are two paths you could see there. And we already looked at everything that's involved in the second path. So what we're going to do, what happens is that from this X1, the next step is to produce logits. So we already looked at what's in the second path. So when you perform that operation and you calculate what X1 is, ultimately where you're going to get to in a one layer LLM are logits right here. And in order to get to these logits, you're going to utilize an unembedding matrix. And this is another weighted matrix. So let's now like kind of like a stack trace work backwards to decompose this using circuits. So if I were to take x1, it looks like this. So we already looked at this is going to be the sum over x0 plus the function h of x0 that we looked at, which is a tensor product. So if I were to show this in here in this equation, it looks like this. And now we could do some operation, distribute the unembedding matrix like that. And we already know a lot of things so far about this that we could substitute in. And we have basically our direct path right there and our head path. This is a very, very simple LLM, this is a one layer LLM where you have two different paths. And sometimes you could go directly in the direct path and bypass the head path. And so we have decomposed this into a sum. So now let's start filling in more information that we know. So we know what the head is. It's the tensor product of the attention matrix in our OV circuit. And then we know that this right here is an embedding matrix. So we could substitute that in. X0 is what we started with, our embedding matrix. So now then we could substitute in or what our h of x0 is that we already know. And then we could do some distribution here. So right there, I'm distributing the unembedding matrix inside of that. We know that this right there, X is our embedding matrix, so you can move that down. The next thing we know is that the attention matrix is calculated using the softmax, using the QK circuit. And we could just pull that down right there. So when you look at this and take a step back, you'll see that I have decomposed this into several different chains. And I've decomposed each path in there, the head path and also the direct path. And each part of this equation tells me something. The QK circuit tells me where, and the OV circuit tells me what. And then when I do this calculation, I get logits back. So this right here is a decomposition over different paths, two paths in this example. Imagine this was more and more complicated. If you had more and more layers, you could basically decompose them in many, many different paths. It's like taking a stack trace of the flow of information in the LLM. And so we started with raw embeddings, then we went to calculated X1, and then we calculated logits. And that was a very simple example of like two circuits, the QK circuit and OV circuit in this paper, a mathematical framework for transformer circuits. Since this paper was released, there has been so much research, and I'll share in my upcoming videos more papers about mechanistic interpretability. And that's about it. Thank you so much.